And yep, it's on the screen. I've already said we've assumed that D is less than B. It's a shallow foundation. And we're going to assume that soil above foundation level there has no strength. The reason we do this is that plants may grow in that realm, and roots may cause gaps in the soil to open up and damage the strength. Similarly, in dry weather, soils can shrink and you can get desiccation cracks. We've all seen riverbeds and things dry out a bit and crack. Anybody seen a clay soil crack? It's also true that when you get freezing, you can get ice lenses form in that zone, and when the ice melts, you can lose strength. So we ignore the strength there because it's a safe assumption, and it's actually a realistic assumption if we think something like a tension crack may form in that zone there. So we're assuming this just acts as a surcharge without extra weight. And we're going to assume a failure mechanism. And what I'm going to assume here is that it rotates about that point there, and a cylinder, it looks like a semicircle in cross-section, but of course it's a strip footing. So it's a cylinder of soil, rotates around like so, and the result is a failure surface around there. And on that failure surface, we mobilise the shear strength of the soil. This type of analysis is called a limit equilibrium analysis. What we're actually doing is creating in our minds this point just before, well, not even just before, just at the point of failure. We're saying what's happened is the soil has been loaded up to the point where it's just about to fail. The mechanism is actually in the process of just forming now, but it's not run away with itself. We're going to say at that point of failure, it must still be in equilibrium. It's not run away with itself. And so we're going to equate the failure stresses on the failure plane to the applied load in order to work out what that limit equilibrium is. Okay, what I should have said was this mechanism, I've chosen it because it's easy to analyse. The geometry of it makes the mathematics straightforward. However, whenever you do any analysis based on a mechanism, and it doesn't matter if you're doing plastic frame theory in structures, which I think you do later this year, or doing failure mechanism in soil, if you guess at the mechanism and you get the wrong mechanism, you guess wrongly, you have an unsafe answer. And so there's always the potential when you use a mechanism to get an unsafe answer. And I've picked a simple mechanism. I'll tell you now in advance, it doesn't give us the right mathematical answer. We'll talk about the mechanism that does in a moment. But I'm using it because it illustrates every concept you need to know about to understand the basis for the analysis, what we're assuming, and therefore what the likely problems with the analysis might be. Okay, so I've labelled that, and in my notes I just labelled that as a potential tension crack due to, say, desiccation. And because a potential tension crack may open up, I want to ignore that strength and replace it with that block of soil just with a weight there, which I'm going to call W soil. So I'm going to take that diagram. Oh, well, the other thing I haven't labelled yet is I call this point of rotation O, a very common notation to use O for the centre of rotation. So I'm taking that and I'm going to idealise it into a false diagram. So I'm going to take that and I'm going to add the weight of the concrete in the foundation to the weight or to the load we're going to apply, and I'm going to put W soil on the other side, and I end up with something, as you've already seen by looking ahead in your notes, that looks like that. So we're saying that that is equal to that Q bar is equal to our original Q plus W concrete. It's quite important to remember that the answer we get out of this analysis includes the weight of the foundation. Remember, the structural engineer, when you're working with a structural engineering team who wants you to design the foundations, will give you the structural loads on top of the foundation. So you have to allow for that. I said it was on the point of failure. We've already said at the point of failure, the soil mobilises a shear strength, which is torr at failure equals Cu. So that allows me to put a shear stress all the way round this mechanism and everywhere, and the direction of the shear stress is opposing the motion. So we're saying that's equal to Cu, and it's equal to Cu everywhere. This is why we've started with undrained soil, because if this were drained soil, we would have an equation that the shear stress equals sigma dash tan phi. So all round there, that's Cu. There is a normal stress. Because it's a circular arc, it will act through the centre of rotation. There's a sigma. It varies. But because we're going to do moment equilibrium, so we're considering something which is rotating, the normal stress has no moment. So, now limit equilibrium, we're saying it's just about to fail. The mechanism has formed, but it hasn't moved yet. So we're going to take moments about O at this point. Take moments about O. And what we've got is the motivating force Q bar. That's a force. To get to moment, we multiply by lever arm. The foundation has a width B. Its mass, or its weight, which is the force resulting from its mass, acts through the centroid of the foundation. Or, if you like, the column is mounted centrally on the foundation, and therefore the lever arm is half the foundation width. So I'm saying the lever arm is B upon 2, and that is the only force causing failure of that mechanism. But it's opposed by the weight of the soil above foundation level times, well, if it's a circular arc, that distance there is also B. So the lever arm is also B upon 2. And we've got to add to that the shear stress around the failure surface, added up over that failure surface to give us a force, and then multiply by its lever arm to give us a moment. So we're going to say it's going to be Cu is the stress. What's the area over which it acts? A half pi b. So what the gentleman at the front is saying is the circumference of a circle is 2 pi r. So the circumference of a semicircle is pi r. You're using the diameter, not the radius, weren't you? Yeah. So what we're saying is it's got to be times pi b. Okay, so that's just the force. The next thing to notice is everywhere around that surface, the shear stress is acting tangentially to the circle. So although the direction is changing around the surface, locally there it's acting tangentially, locally its lever arm is B. Go to the next bit. Locally it's acting tangentially, locally its lever arm is B. So the lever arm is B. So what we can say from that is Q bar equals W soil plus 2 up there, 2 pi B Cu. And that is the bearing capacity of that foundation on that mechanism. So in 2 lines, we've got to the answer, which is why I chose this particular mechanism. So for those of you who still, I'm cancelling a B in each term. I'm multiplying each term by 2. So I lose the B over 2, I lose the B over 2. I get a 2 over there. Yeah. OK. That is the answer. I'm not going to pretend there's any more to getting the answer, but we want to work in a general form which is applicable to any situation. And so we tend to write this equation not in terms of load, we write it in terms of the pressure we can apply to the foundation soil. That's a convention. So I'm going to write it as an ultimate bearing pressure. This isn't part of the analysis, it's just trying to write it in a standardized form. Ultimate bearing pressure, which is equal to Q bar upon A, and I've used Q lowercase alt, and I put the bar above just to remind us at the moment that it's this combined structural plus foundation weight load. We'll drop that bar immediately in standard notation. That's just there to remind us what we've got. And so we divide through by A, and we're dividing by, remember, it's the base area of the foundation, because we're trying to put that term there, Q, we want to write it as Q ultimate, and I say at the moment we've still got a bar above it. So all we want to do is divide by the contact area, which is equal to B times 1. And what we get is W soil upon B plus 2 pi Cu. And we tend to write this, we call that Q naught, which is the surcharge load, the surcharge pressure, and so therefore we tend to write it as Q ultimate equals Q naught plus 2 pi Cu. And that's the standardized format we tend to write the equation in. I've done that out on the projector because I find developing the ideas logically at the speed at which I think is a better way to do it than to have it just come down, blink, blink, blink on an overhead projector on the screen. But I have now got a sort of, if you like, the neat version of the same thing, so you can see it again as we quickly go through to keep the notes up to speed. So what we've said is we've got that picture there. We said the soil above foundation level. Is it because I've moved on too quickly? Is this what this is about? Yeah, I've got a question. Good.
You know on the bit before, you know where you divided it by the area?
Yeah.
Why did you take the area just to B?
OK. There seems to be 2 good reasons for going back a step. The reason I wasn't too worried about moving on quickly is this is a repetition, so it's reinforcing an idea. But let's go back to here. The first thing is, anybody who wants to get some notes down, do so. But do rest assured, it was all there coming up again. And now I've been asked, why have I divided by B, the area? So what we've got